So let's look at another equation that governs incompressible flow, and this is Bernoullis equation. Okay, so while the continuity equation also holds in this instance, we also, if we look at a similar system where we have, two different cross-sectional areas, A1 and A2, we also notice, so we know that the water is going to be going through at two different velocities, V1 and V2. And we'll say that these are different heights above some reference, Y1 and Y2. We'll call this our reference where y is equal to 0. Okay. What Bernoullis equation tells us is that the pressure plus 1/2 the density of the fluid times its velocity squared plus the density times g times h is equal to a constant. So this is Bernoullis equation. So if we look at something like this pipe with fluid flowing through it, we see that we have P1, the pressure coming in on the left, plus 1/2 the density of the fluid times V1 squared, plus the density times G times Y1 is going to be equal to the pressure at the other end, P2, plus 1/2 the density of the fluid V2 squared, plus 1/2 the density G times Y2. Okay, so now we see that we have, a term with pressure, a term with velocity, and a term with height. And so we see that these are going to be the three main factors in what the overall pressure of the system is, because these combined terms are going to be the same everywhere throughout the fluid. And so I recommend looking at some of the problems in Halliday-Resnick-Walker on this section, because these are, a lot of these are fairly typical problems, but there are going to be some, kind of interesting conceptual problems too. So I would also look in Professor Bodek's notes, because he talks about some of the conceptual problems, and make sure that you do the conceptual problems in Halliday-Resnick-Walker, because you will have one of those, at least one of those on your, on your fluids exam when you take it.